Okay, good morning. So I guess in short the message is if you want good service in the labs, choose a session where there are under 100 other people, right? So you can see that on the course, I guess, course listing of Sproul Hall. You can see how many are enrolled. If you're in one of the sessions where there are lots of people and you have time for another one where there are fewer ones, you will probably get a much better experience because you will have almost a personal tutor instead of having to share with other 30 students. Okay, so we're actually today we're going to talk about circuit components, right? What we talked about so far was maybe somewhat interesting but not very useful. We have to put real circuits into our electronic devices to make them do interesting stuff. But before getting there, I just wanted to do a very quick summary. I wanted to tell you what I expect that you now know. Okay, and so that's stuff that we're going to use from now on, and I just assume that you know it. So if you don't, come and ask us in the office hours, and also, of course, it's going to be on the exam and so on. So let's quickly go over this. So I expect you to know about schematics. So those would be things like this. Schematics have nodes and branches. How many nodes does this schematic have? 3, okay. How many branches? 4. All right, so first bullet point already done with. Identify currents and voltages. This here, would this be a current? It would be a voltage, right? Here, for example, we could have a current I1, okay? And you know these symbols? Probably you do, I hope. Calculate unknown currents. So, for example, if we, let's say if we had a current I1 and I2 and we knew both of these what they are, could we also figure out what the current Ix here is? Why would it be I1? What are you going to use in order to figure out that it's I1? Yeah, Kirchhoff's current law, right? Maybe you could also have said, well, it's obvious or so, but deep down, right, you just know Kirchhoff's current law already well enough that maybe you see that this is obvious. Maybe this one isn't quite as obvious. Iy. How would we figure this one out? Right, so now we really have to use Kirchhoff's current law. We would, for example, sum all the currents that are leaving this bluish shape here. So that would be minus I1 plus I2 minus Iy equals 0. Okay, and then you can solve for Iy. Why does it have a few minus signs? Exactly. These. Hey, please, not always. Although, in fact, I would like answers from the back, right? So these currents are actually entering the node; they're not leaving the node. So we need to put this minus sign. All right. Well, we could do the same for voltage. I'm not going to go for Kirchhoff's voltage law now because the schematic already looks bad enough. But suppose that we actually knew. I need to make this a little bit nicer. So here we have voltage V1, right? And here I have a minus sign, here I have a plus sign, here I have current Ix. So the power in that component is equal to V1 times Ix. Question, price question. Is this the power that this component delivers to the rest of the circuit, or is this the power that this component absorbs from the rest of the circuit? Okay, I actually need to look at it. So that would be power that it delivers, huh? Okay, that would be active sign conventions. So I expect that you know these sign conventions and can apply them. All right, and then you need to know about energy, which is power times time. All right, so that's what so far what you should have learned. All right, so we already started talking about circuit components. So in a nutshell, there are at least hundreds of thousands, if not millions, of different circuit components. And from one single vendor on its website, it says it has 450 different ones, right? So now if if circuit design was learning 450,000 different circuit components, I wouldn't be in this business. But fortunately, all these circuits, although complicated, they really are made up out of a small number of relatively simple parts, or at least a small number of parts. Some of them, transistors, can be pretty damn complicated, but we'll see even in many ways, in many cases, even transistors behave quite rationally and actually are quite simple. So I gave you a couple of examples, right? One of them, an entire big supercomputer made out of just two different types of components plus wires, right? So that really works. All right, so where are we going to start? Well, one thing that, of course, is needed everywhere is a source, right? You can't build an electronic system that doesn't have some kind of a source of power. It's not going to do anything. It would be nice. People are trying, right? Energy scavenging, God knows what, but then you just have an energy scavenging source or whatnot that takes energy out of the environment. Who knows what. Okay, but sources, we definitely need them. Typical examples are a battery, a power brick, a wall outlet, and so on. You may have a few more examples. But now we already again have a second problem. Real components are fairly complicated. If you think about a battery, really what a battery should do, well, it should supply its rated voltage, right? 3 volts or something like that, right? Or 1.2 or so. But it sort of does that, but in reality, of course, the amount of the voltage of a battery, it depends on the current that you're pulling. If you have a small battery, try to pull an amp, well, the voltage is not going to be the 1.2 volts or so that it's supposed to be. It's going to be a lot smaller. Most batteries, the voltage that comes out actually depends on things like temperature. It even depends on age, right? An old battery, you have never used it, but the voltage for some reason is almost 0. So models for these things, of course, very complicated, right? And so that's not very practical. So we take a simple way out. Instead of modeling this complicated stuff, we simply say, we model just an ideal source. Well, that does have one drawback. Ideal sources don't exist. Nothing ideal exists in the real world, and here we talk about the real world, right? But the advantage, of course, is that now it gets really simple. And the other good thing, it's actually not only simple, it's actually useful, because even though it's an element that doesn't exist, very often its behavior, the ideal behavior, is close enough to actually allow us to design and analyze circuits. And in other cases where we actually need to maybe we want to actually model that the voltage of the battery or the source drops a little bit as the current increases. Well, it turns out, we'll see later, that if we add some other components like resistors to the ideal model, then we can synthesize a combined thing that actually behaves very much like the real one. So even though we're going to talk about ideal elements, and they don't exist, and we'll continue to do that, we still can design practical circuits out of them. And it's a lot easier than if you had to describe the real behavior. All right. So, well, here we start with an ideal voltage source. Give it a symbol. It's very important. So we give it not. We could just use our generic rectangle, but that would be inconvenient because then we always have to write some text next to it. Actually, that rectangle here is a voltage source, so we use a special symbol. We give it a name, and sometimes we also write the value of that source right next to it. Okay, so now we can describe this ideal voltage source mathematically, or we can describe it graphically. Let's start with the graph. On the right side of this slide, I've already wrote the axis, current and voltage. How would the characteristic of an ideal voltage source look on this graph? Maybe somebody from the back. What do you think? What it would look like? What does it actually say? I have an ideal voltage source. Its value is 3.3 volts. Well, what it really says is that, look, the voltage between the terminals of this thing this voltage here is 3.3 volts. I guarantee you it's 3.3 volts no matter what. In particular, I don't care what the current is that is flowing. The voltage across me is 3.3 volts. That's really what it says, okay? the ideal voltage source. So now, can we describe that on this graph? Well, if, for example, the current was 0, let me use another color. If the current was 0, that will be here, right? The voltage would be 3.3 volts. If the current was 10 amps, the voltage would be 3.3 volts. If the current was minus 10 amps, the voltage would be 3.3 volts. Okay, and so actually I should tell you which current I mean. I mean actually this is the current I, and this is the voltage V here. Okay, so now a little quiz question again. Suppose actually the current here was 10 amps. So I'm at this point, suppose, right? How much power is this source delivering to the rest of the circuit that I haven't shown there? 33 watts, right? Okay, so now we could, of course, also end up here, minus 10 amps. And we are in this point now. What's the power that this source is delivering to the rest of the circuit? Yeah, minus 33 watts, right? So again, be very careful. This was nothing new. That's what I just on the previous slide told you that you know by now. Hey, you know, sign conventions tell us that the power delivered is for that, that's active sign convention, is simply the voltage times the current. Well, we get a negative number. A battery absolutely also can absorb power, right? For example, if it's a rechargeable battery, then it maybe will use that to deliver that power later. If it's not a rechargeable battery, maybe it gets very hot or whatnot. Okay? So now we can express, so we've expressed the relationship of our battery or of ideal voltage source. We have expressed that graphically. We can also write that algebraically. That would be the voltage is equal to V1 and the current is arbitrary. No matter what the current is, the voltage is 3.3 volts. Okay? It's almost like a contract. Okay, so now we can actually already start using that. And one particular example is the short circuit. Short circuits are very often actually used. I mean, there is also one case of a short circuit that is probably infamous, and that is the short circuit that we put here. What does it mean if I short circuit that supply there, that outlet? It means that I put basically a wire across it, right? Okay, and so possibly infinite, well, theoretically infinite current, and then the fuse flows, right? And maybe I get an arc or so, and maybe burn myself. Okay, but what's the voltage across a short circuit? 0, right? Exactly. The voltage is 0. A short circuit is simply a special case of a voltage source where V is equal to 0 and the current is arbitrary. Sometimes it's very large, obviously, if I go and put my short circuit across there. And, well, what's a reasonable symbol for a short circuit? Well, a complicated one would be V equals 0, right? That's actually a short circuit. But of course, simply a wire would do also. Okay, so now we know formally what a short circuit is. I is arbitrary. I'm not going to write this long word again. Okay, so let's do some other examples. Here we have a circuit that actually has 2 voltage sources in here, and we would like to know this. We would like to know the voltage across this other component X1. How are we going to do that? We're going to use which law? KVL, right? Okay. So what would we write here? Well, we enter this terminal at the negative, at the minus. In fact, I should, of course, if I did this right, I would put symbols here. So I enter there at the negative sign, so it's minus V1 minus V2 plus Vx. Well, it's okay. All right, equals 0, so that would be equal to Vx is V1 plus V2, or 3 plus 5 volts, so that's 8 volts. Fine. Now, here is one for you, and I notice I've already put an arrow here. Be careful, the symbol, I flipped it around. So now what you're going to do is, some of you anyways ask, who is going to be my lab partner? I guess we should get to know each other. So go and talk to your neighbors, maybe 3 together. Appoint somebody who is going to answer, because I'm going to ask somebody, maybe even from the back. And you figure out what is Vy. All right? Okay, so you have a minute or two. Please do that. You have a question? You know the answer? You what? I think that's right. Right? Okay, who has not yet figured it out? Maybe could I have maybe it's the Berkeley T-shirt all the way back there. Could you? Yes, yeah. Negative 2 volts, all right. Who wants an explanation? Apparently nobody, so we figured that one out. Yes, okay. Oh, if it's not given, that's really bad, right? If for example, I'm not sure whether I understand your question, but if I just said this is a voltage source, but I don't tell you where the plus and the minus is, it's not good. Okay, this element here, like X2. Okay, so you need. I can. That would be a really unfair question. I can ask you what is Vy, right? Because I told you where the plus and where the minus is. I could also ask you what is Vz. I could ask that, and you would get plus 2 volts, right? Because I drew the symbol the other way around. But I could not ask you just what is the voltage, because the answer could be it's 2 volts or minus 2 volts, right? So whenever you mark up your schematic, you get the choose signs. You could have chosen the Vc. That would have been fine. And then you just would have gotten plus 2 volts instead of minus 2 volts. But you have to make a choice, okay? Okay. All right, good. So that was ideal voltage source. Now ideal voltage source you can go, I mean, a battery is not quite ideal, but it gets reasonably close, right? We argued that already. You can go buy one, you know what it is. Now, mathematically, there is nothing special. If we can define an ideal voltage source, of course, we can also define an ideal current source. Practically, it's a little bit more difficult because you can't go to the supermarket and buy an ideal, or even any current source for that matter. But there are 2 reasons why current sources make sense, ideal ones, anyways. One of them is that many devices actually behave like current sources. For example, transistors, the most prevalent circuit component in the world, right? Billions on one chip. Actually, transistors, when they are operated in certain ways, behave like current sources. There are many other cases. And the other thing is that actually very often for many things, we actually need current sources to realize them. And finally, we can use, for example, then a transistor to simulate that current source, to synthesize a current source. And then there are also some, we will see shortly that there are sort of some some almost mathematical things, how we describe circuits. Often current sources turn out to be really handy how to describe them. So let's just accept that we can define a current source and figure out how to build them later. So again, we have here the characteristics. This current source here runs a current of 6 microamp, and again, of course, that means that the current is running in this direction, the direction of the arrow. I have to tell you, otherwise you can't guess it. You have a 50% chance, right? But I could be mean. That would, well, just makes no sense. Okay, so again, that of course means now that the current is 6 microamp no matter what the voltage is. So I equals I1, V is arbitrary. Okay? It's again sort of a contract you want. Okay, and so just like for the voltage source, with the voltage source actually we can simulate a short circuit. With the current source we can actually simulate an open circuit. Well, what's an open circuit? How would we define that? Yeah, the current is 0. No matter what, no current flows. That's an open circuit, okay? So that's the definition. I is equal to 0. V is whatever it wants to be. And of course, the symbol would be either we have a current source where I is equal to 0, or we could as well just not draw anything. Then no current would be flowing either, right? So how would we represent this? Well, the voltage can be anything. I can travel here as much as I want, and the current 0. So we've defined open circuits and short circuits. They're very, that's jargon that's often used, so that's helpful. But now let's talk about something that is actually important, that a problem that we very often have. So there are these things called LEDs, light-emitting diodes. Without doubt, you have seen them. For example, the backlight in your computer. God knows what is it? Well, it's LEDs. Okay? So also some of the watches or so that you have, they have LEDs and so on. So light-emitting diodes. So now here I've shown the characteristic of a light-emitting diode. So what happens is that if initially the voltage is 0, the current is also 0. Well, not surprising, right? How could that thing somehow generate power? Okay, so then as I increase the voltage, current starts flowing. But very, very little current, okay? And also no light comes out. Then approximately here, it starts getting lit up, but it's fairly dim. Then the current increases like crazy. It gets bright. And then here, you know what it does? Any guess? Here it burns up, okay? So it's very important. If we want an LED, it's very important that we operate this thing here. If we are below, well, no light comes out. And if we are above it, the thing is dead, right? So not very good. So we have to come up with a circuit design that makes sure that we are always in the red region. In fact, we do not even want to be anywhere in the red region. We want to be just at the right brightness, because, of course, you wouldn't like it if your laptop, the backlight, would continuously vary and so on, and sometimes a little bit more, sometimes a little bit less. That would be very impractical, right? So how are we going to design this? Well, here are two ideas. For circuits that we could use to power this LED so that it provides a nice constant backlight for our laptop. So here, So here's circuit A, circuit B. So let's look at the circuit A first. Well, we have a voltage source, V1, that is across that LED. Consequently, voltage across the LED is what? It's constant V1, right? And we can, of course, adjust V1 by picking the right voltage source. How would we represent this? Well, the voltage is V1 no matter what the current is. So let me show this. The voltage, let's pick the voltage somewhere here, right? So that this thing actually has a chance of putting out light. All right? Okay, so if the voltage has this value, whatever this is, approximately 3 volts for a typical LED. Okay? Whatever. So approximately 3 volts, and then the voltage source, I just want to be here. The LED says, oh, I want to be here, and then the compromise is where they intersect, okay? So that's going to be the current that flows, whatever, a milliamp or so, okay? Now, with really ideal components, we're done. That works just fine. You just got to adjust the voltage here just to the right value, and then everything works fine. In practice, things don't work so well because, again, as you know, real batteries, of course, they get older and older, and then this yellow line shifts to the left, and what happens to the LED? It gets really dim, and then you charge up your battery, and this thing moves over here, and what happens to the LED? If you're lucky, it gets really bright, and if you're not so lucky, you need to buy a new laptop. Okay? So, well, we could do that. Would we become famous as circuit designers? Well, maybe infamous. Okay? So let's come up with the right solution. So this time, we have a current source that pumps out current I1, and we can again adjust this current. Anyways, the current source has then a characteristic that looks like this. And the value of this current is I1. Okay? So where does this thing operate? Well, it operates in this point here, again, where the intersection is. It doesn't have to be where the yellow line is, right? But, so that would be sort of our choice. Now let's imagine that this current source also has some variation, right? Sometimes it's a little bit less, the current, and sometimes the current is a little bit more. What will happen? Well, the light will get a little bit brighter or a little bit dimmer, but not a whole lot. And it will not just burn up unless the current source suddenly puts out twice as much current or even 5 times more current or so. Right? So this is an example where the voltage source really doesn't cut it. Don't do that, right? And, but with the current source, we can solve the problem very nicely. And we'll find out how we're going to do that actually in the lab very soon. Okay, so current sources are useful. Here is just a fun example. Actually, this was on the homework, right? So let's not do that. I'll leave that for you. Okay, so there is one problem with ideal sources, and that is you can put stuff together that you can't build because there are no ideal sources. So this is an example here, right? You put the voltage source that says, and the voltage across my terminal is 3 volts, no question asked. And this one says, but no, the voltage across my terminal is 6 volts, no question asked. And of course, it's incompatible. And because of these two elements sort of both are totally single-minded, the thing doesn't work, right? Now, in practice, it won't blow up because, again, ideal components don't exist. You can't build that, right? Of course, you can go and buy a battery that has 3 volts and another battery that has nominal rating of 6 volts, and then you can put them together and perhaps a large current flows, but the current will be somehow defined by the internal resistances of the batteries. With ideal components, you just can't build this. I can draw it, but it makes absolutely no sense. The same thing for these current sources, right? You can't have, in a single wire, have simultaneously flow 3 milliamps and also 7 milliamps. It's one or the other, okay? So I'm not going to bother ever drawing this anymore unless I make a mistake, and I suggest you too don't bother with that. Okay, fine. So one more component that we need. We need this one more component, then we can start building really useful stuff. It's actually not so terrible. I'll show you that people make a career out of just resistors. Maybe they need a source, right? Because if no current flows through the resistor, it's not that interesting. All right, so resistors, I've heard about them in physics. They're very important components. They model a lot of different things. For example, a cooktop, simply a resistor. A light can be modeled as a resistor, and so on. And then, of course, there are resistors that we have in the lab, and we use them for circuit design. So resistor has this zigzaggy line as as a symbol. We can again define currents and voltages across the resistor, and of course we can give it a value. The value of resistance is measured in ohms, and this one has, for example, 4.7 ohms, or k ohms, kilo ohms. Why actually 4.7 kilo ohms? We'll see that very soon in the laboratory. Of course, in principle, you can make resistors of any value, but then you would have to have a circuit cabinet of infinite size. That would be a little bit too large. So in practice, people make some reasonable choice, and 4.7 k ohm is one of them that you will find in a well-stocked circuit cabinet. Okay, so well, what's the relationship of a resistor? Well, a resistor basically says that the current that's flowing is proportional. The voltage across the resistance is proportional to the current that's flowing. Okay, and the slope of this line is the resistance. Okay, well, we can capture this mathematically also, right? The voltage, we said, is equal to the resistance times the current. And this thing is called Ohm's law. Okay? So actually, I should have said, here are a few examples of resistors. You're going to see those in the lab. Why, typically something like this, most often. Why? What about these things? Why are they so big? Actually, they are actually big. You can maybe see this. Why are they so big? Yeah. Well, could be. I'm not sure whether this one is. This one, at least, it's big and not adjustable. Why would you make a resistor big? Yeah, exactly. Hey, if this has an ohm, 1 ohm resistance, and you put 100 volts across, there's a lot of current flowing, right? And then it gets really, really hot. Okay? So especially small valued resistors, they have to be fairly large so that the heat somehow can get away. On the other hand, if you use a resistor and you want to put it into a small electronic gadget, like a hearing aid or so, right? Then you want a really small resistor, and so there are resistors, I need a magnifying glass to even see them. Okay? So there are lots of resistors available, and again, we've characterized them here now mathematically and with the graph what they're doing. So I already said unit is ohms or omega. They're made out of all sorts of different things. Usually the same, very often the same material as we make wires out of, copper or so. Instead of making a really wide copper wire, we make it very, very thin, and then it doesn't conduct current so well. Well, then it's a resistor. Maybe we don't use copper, some other materials. The values that when you buy resistors, so you can get them from milliohms or so up to maybe 100 megaohm. What happens if you want a resistor that has much higher value, very, very high value? It's actually a very interesting thing in the laboratory. When you touch the component, your hands are a little bit sweaty. Okay? What is sweat made out of? A little bit of water and salt, right? Yeah. So water and salt, that's ions, that's actually conductive. So you pick that component, you put the thin film of sweat on it, and current can flow through it. And what's the resistance of that thing? Well, a few hundred megohm. Okay? So getting a resistor that has much higher values, so it's kind of difficult. You have to wear gloves if you solder it or so. Okay? But we're not going to use those. But it's just in practice, it's hard to make resistances that are much, much larger than maybe 100 megohm. Yeah?
I don't understand. Well, why is the problem if it has a high resistance and you're handling it?
So let's assume that this was our resistor here, and its value was, let's say, 1 gigohm, so 10 to the 9th ohm. Okay? So now you grab it and you put a film of sweat on it just by holding it. Conductive path, exactly. So now suddenly you have another path for current to flow. It doesn't care that there is a resistor also, it just flows through the conductive path. Okay, so those are just sort of tricks of the trade or so. All right, so now here is Ohm's law, and we have an example. So the first example, again, we do together. The second example, we will be able You'll have to do it yourselves afterwards. So here we have a current flowing. The value of the current is I1. We have a voltage across the resistor. The value is V1. Consequently, we can, before we had said V1 is equal R1 times I1. We can solve this, right? That's Ohm's law. Solve this. We get V1 over I1. So that's 8 volts over 4 milliamps. That's 2 k ohm. Okay? Fine. So, now you have a minute to do the thing on the right. Please, again, talk to your neighbors. So there is a little trick in it. So go figure that out. You already know the answer? Have you drawn the arrows? Okay, so probably some of you figured it out. Some may have still questions. So let's figure out who has the question. Maybe who's with the nice bear shirt back there? Did you figure it out? Well, it says bear, right? Yeah, exactly. Now you turn around. You say bear on your shirt, or I cannot read it. Well, maybe somebody else you have sort of a bluish, or like a river on your shirt?
It's going to be negative 3 k ohms, but it seems weird because the 6 volt potential difference should be flowing the other direction.
Okay, something is bizarre here. All right, but you got the right answer. So let's figure out how we do this. Okay? So, well, the voltage across here is V2, right? The current here is I2, but Ohm's law, here, Ohm's law is defined for the voltage and the current both going the same direction. That's how Ohm's law is defined. If I were to define Ohm's law, R equals V1 over Ix, what would I have to introduce? Well, I flip the sign of Ix, or of I1 to get Ix. So in order to get, again, the same result, I have to introduce a minus sign into my equation. Okay? Ohm's law is defined much like active and passive current sign convention. Ohm's law is simply defined for voltage and current going in the same direction. If I make them different direction, then Ohm's law has a minus sign, or alternatively, I of course can define here an I2 prime that has which value? Minus 2 milliamps. Okay? And now I can calculate what R2 is. It's simply YV2 divided by I2 prime, and that is equal to 6 volts over 2 milliamps, so minus 3 k ohm. Okay? Yes?
What does the negative resistor do in the real life?
In the real life, it delivers actually power. Okay? A real resistor would, the IV characteristics of the real resistors, of the negative resistor would look like this. So we actually deliver power. In this quadrant here, the element delivers power. In this quadrant, it delivers power. In these other two, here and here, it absorbs power. So now you may say, well, this is only a trick question. And in a way, you're right. I just wanted to make sure that you can apply the sign conventions correctly. Just apply the thing and get the correct answer, right? And that may go against your intuition. You may say, well, gee, come on, give me a break. Where is that negative resistor? And yes, if you go to your closet and you look at all the resistors, you will find lots of different values, but they're all positive. You won't find a single negative one. But on the other hand, we will see later in the course, we can actually build negative valued resistor. Now, is that a trick? Again, just something to keep us busy because I have more interesting questions to talk about? Turns out, not at all. Not at all. You all own plenty of negative resistors. You just didn't know it. Now you do. So if you want to make a clock, for example, imagine your big old grandfather's clock. Right? It has this pendulum that swings back and forth. Okay? And you can kick it once, and then it swings for maybe a minute or two, or if it's a really good clock, maybe for an hour or whatnot, and then it stops swinging, right? So you actually have to wind that clock with big weights or whatnot. You have to wind that clock. So there is a mechanism in it that makes that clock from stopping to tick, right? Well, now in your computer, lo and behold, it needs a clock also, or your phone or so, it needs a clock also to operate. Not just to display the time, but also to run the CPU and to do the communication and whatnot, right? So it has a clock inside. Now, it doesn't have a big grandfather's clock inside. But it actually had something that is remarkably similar. It uses a quartz crystal that also moves back and forth, usually a little bit faster, maybe 10 million times a second or so. So a quartz crystal does exactly the same thing. And just like that big grandfather's clock, you can kick it, and it will start moving. And then it will maybe move for a tenth of a second or so, and then it will stop. Right? The amplitude will get smaller and smaller, and ultimately it stops. Actually, it decays exponentially. Why does it stop? Well, because it dissipates power. You can model, actually, this dissipation by saying, well, this crystal that moves, so that grandfather clock that moves, looks like a resistor that dissipates power. A totally normal positive resistor. We don't want it, but nobody ever figured out how to make a clock that doesn't stop if you keep kicking it. Okay? So then how could you get over that? How could you fix this problem that the clock doesn't stop after tenths of a second all the time? That would be very painful. Yeah, you don't know. Okay, fine. But what is that mechanism? You need a mechanism that supplies the power that stupid resistor that we didn't want, or the friction in the grandfather clock, always dissipate. You need that, right? In the grandfather clock, it's this big weights. In the electronic circuit, it's a negative resistor. See, if you have a circuit, here I have a resistor, and it has some value, let's say 3 k ohm, plus 3 k ohm, right? But I really don't want any resistance, right? Because that resistance dissipates all the power, makes my clock to stop. Well, I put another resistor in series with it that has minus 3 k ohm, and the total resistance, we'll see that just on the next slide, actually, the total resistance of this whole thing is 0. Now, of course, again, you can ask the question, well, that's a great idea, but where am I going to get the minus 3 k ohm resistor from? Well, that's what we have EE40 for. You need to wait another few weeks, and then we'll have our negative resistor. But that's what is inside your phones, your computers, all of that. Negative resistors. Okay? So in those circuits, it looks like this. And if you calculate it right, you actually find that the resistance negative, lo and behold. Of course, you need a battery for that negative resistor to operate. It's not just a simple component with 2 terminals. Behind it there is a whole bunch of circuits, right? So that's why we are not designing it today. Was that your question? Or?
Yeah, more or less.
You still can ask it?
Well, would it be like time varying? Like inside, you say it's 0, this is going to be 0, but then like if we abstract, you can say outside, so inside keep going back and forth?
Okay, yeah, so now we are getting into oscillator design. I will show you how to build a negative resistor. I won't show you in EE40 how to actually make a real electronic clock. Okay? So, or at least not this way, not with a quartz crystal. So if you really want to know, you have to take a few other courses, and ultimately you end up in EE143, and probably there we're going to tell you. Okay? But yes, adjusting the value of that resistor is kind of a tricky business, because if it's too small, well, the clock will stop anyways, right? It will take longer, but it will stop. If it's too big, then the clock will go a little bit more, a little bit more, a little bit more, and then if it's a grandfather clock, something terrible happens, right? Okay, so.
So it's not really a negative resistor you're talking about, but rather set of components that behave like a negative resistor?
That's exactly right, yes. Yes. The whole thing, it's let's say, if I would make a black box and I would put in a whole circuit that includes also battery, I would give it to you and I would say, go to the lab with it, figure out what it is. You would make all sorts of measurements. You would say, you know, it behaves like a resistor of value minus 3 k ohm. Yeah.
So basically the resistor is just somewhere in the resistor there is another voltage source that is bigger than the voltage.
Right. Yeah. That's supplying the power. Mm-hmm. Yeah. So in fact, that is something very useful about circuits anyways, that will sort of come naturally, right? We show symbols like this. Here we show, for example, an ideal voltage source. Well, in practice, probably there is not an ideal voltage source inside your computer or so. It's probably not even just the battery. The battery may have 16 volts, right? But the circuit that you have may use 8 or 3 or 1 volt or so. So there's a whole pile of circuits that may be very, very complicated that actually go from the battery and actually make these 8 volts, right? And regulate it and God knows what and so on. But here we are just interested in the fact that we have 8 volts. We are not interested in designing this right now. Later in the course, we can design this thing, and then this thing suddenly will explode and will fill the entire page with all sorts of components or so. But not just yet. Huh? I don't want to confuse you too quickly. All right? So circuits can be sort of hierarchical, even though I put here only the symbol of a resistor. That basically says it behaves like this. But how do I build it? Well, I haven't told you, right? I don't need to tell you. At this point, I only tell you that's how it behaves. Very often when you buy a component, you look at the data sheet and you don't know how it's done inside. Maybe a bloody miracle, but if it behaves the way it's described. After all, if you had to know exactly how it works, you wouldn't make many cellular phone calls, right? Okay. Any more questions? Let's try to do one more thing before we break for today. Okay, so very frequently we will run into situations where we don't have just one resistor, but we have 2 or 3 or whatever. And so here we have 3. And usually there is a reason why we don't have 1, but we have 3. But again, circuits with really lots of resistors, they quickly get complicated, we get confused about them. So there is the question, could we somehow replace these 3 resistors with just one that behaves as if we had all the 3 resistors there, okay? So let's try that. Well, what does it first of all mean that it behaves like it? Well, it means that if I have a voltage V1 across all 3 resistors here, and I have a voltage V1 across this equivalent resistor, then the current flowing in both situations should be the same, right? Then it behaves the same. You have a question? Ask it, otherwise. Okay, so we want that these 2 situations behave exactly the same. So the currents and for the same voltage, the current should be the same. All right, so let's figure out what the voltage is in the left case. Well, that would be V1 is equal to R1 times I1 plus R2 times I2 plus R3 times I3. I'm just using Ohm's law, and if you forgot it, two slides back, right? I, of course, can write this as R1 plus R2 plus R3 times I1. And this was totally stupid. I1. These are all I1s because the current through each of these resistors, of course, is the same, right? Can't escape. Okay, well, now for the resistor on the right side, the voltage is simply equal to Req times I1. So in other words, the value of Req is equal to R1 plus R2 plus R3. In other words, if I choose that value for Req, I can simplify my circuit diagram by eliminating the 3 resistors, replacing them with just one single resistor, Req. So, and the other important thing in here is that not only resistors in general, we can arrange components in series with each other. Like here, we can see that they are in series. What does it really formally mean? Components in series means that the current running through them is the same. Okay? Every component has the same current running through them. If I had, for example, an additional jog here that ran off somewhere else in the circuit, the components would no longer be in series because there would be current running here, and then the current through resistor R1, R2, and R3 would not be the same. But if I don't have this, they're in series. Okay? Well, see you Friday already. Gee.